Basic question. The Gallup poll asks a probability sample of 1,785 adults whether they attended church or synagogue during the past week. Suppose that 40% of the adult population did attend. We would like to know the probability that an SRS of size 1,785 would come up within plus or minus 3 percentage points of its true value. So part A asks, if p hat is the proportion of the sample who did attend church or synagogue, what is the mean of the sampling distribution of p hat? What is its standard deviation? So the mean is the same as p hat, which would be 40%, because it gave us that in the problem. And then the standard deviation is the square root of p times q over n, which is your sample size. And we get 0.0116 for the standard deviation. Part B asks, explain why you can use the formula for the standard deviation of p hat in this setting. And this is because we follow the rule of thumb number 1 for proportions, which means that the population is at least 10 times the sample size, and we know that it is because there are a lot more than 10 times 1,785 adults in the US. Part C says, check that you can use the normal approximation for the distribution of p hat. So, to do this, you do n times p, which was 714, and n times q, which was 1071, and we get that both of those are greater than 10, so we can use the normal approximation. Part D says, find the probability that p hat takes a value between 0.37 and 0.43. Will an SRS of size 1,785 usually give a result p hat within plus or minus 3 percentage points of the true population proportion? So to do this, you have to do the z-score formula with both 0.37 and 0.43. So you do 0.37 minus 0.4 over 0.0116 because that's our standard deviation. And then you also do 0.43 minus 0.4 over 0.0116. And when you do that, you get that z, the lower z is negative 2.586 and the upper z is 2.586. So you have to find the proportion between those two, which you get to be 0.994. And that means that over 99% of the samples give p hat within 3% of the true population proportion. Now time for the advanced question. Researchers were interested in comparing two methods for estimating tire wear. The first method used the amount of weight lost by a tire, and the second method used the amount of wear in the grooves of the tire. A random sample of 16 tires was obtained. Both methods were used to estimate the total distance traveled by each tire. The table below provides the two estimates in thousands of miles for each tire, and it also provides the difference in those estimates. Part A says construct and interpret a 95% confidence interval for the mean difference mu in the estimates from those two methods in the population of tires. So to find bar x and the standard deviation, first you plug all your values, which are the difference values, into L1, as you can see here. Then you go to Stat, Calc, one variable statistics, make sure the list says L1, and hit calculate. From there, we can see that our x bar is 4.5563, and our standard deviation, which is Sx, is 3.2255. Next, we have to do a one-sample t-test to find the confidence interval. So, how do we find t? Well, t is going to equal 2.131, and your degree of freedom is 16 minus 1, which is 15. To find t, we have to use table B, and I'll show you how to do that here. So let's hop into the table here. So the first thing you're going to do is go to where it says 15 on the left side, where it says degrees of freedom, because that's how many you have. You do 16 minus 1. Then you go all the way over to 95%, which is on the bottom part of that table, and find where the two meet. and that value is 2.131. Once you find that value, you can plug it into your confidence interval formula, which is x bar plus or minus t star times the standard deviation over the square root of n. So we get 4.5563 plus or minus 2.131 times 3.2255 over the square root of 16. So after doing some simplifying, we get that 4.5563 plus 1.719 equals 6.275. And we also get that 4.5563 minus 1.719 equals 2.837. That means that we are 95% confident that the interval from 2.837 to 6.275 in thousands of miles captures the true mean distance. AP question. Golf balls must meet a set of 5 standards in order to be used in professional tournaments. Of these standards, one of these standards is distance traveled. When a ball is hit by a mechanical device named iron Byron, with a 10-degree angle of launch, a backspin of 42 revolutions per second, and a ball velocity of 235 feet per second, the distance the ball travels may not exceed 291.2 yards. Manufacturers want to develop balls that will travel as close to the 291.2 yards as possible without exceeding that distance. A particular manufacturer has determined that the distances traveled for the balls it produces are normally distributed with a standard deviation of 2.8 yards. This manufacturer has a new process that allows it to set the mean distance the ball will travel. Okay, so part A asks if the manufacturer sets the mean distance traveled to be equal to 288 yards, what is the probability that a ball that is randomly selected for testing will travel too far? So, let's set D to be the mean distance of balls. So we know that they're normally distributed with a mean of 288 yards and a standard deviation of 2.8 yards. We have to find the z-score of the mean being 291.2. So we do z is greater than 291.2 minus 288 over 2.8. So we get a z-score of 1.14. So, and then to find the percentage that'll be over that value, you have to find the complement of the z-score. So we do 1 minus 0.8729, and that gives us 0.1271. So we have a 12.71% chance that the ball will go past 288 yards. Part B says, assume the mean distance traveled is 288 yards and that 5 balls are independently tested. What is the probability that at least one of the 5 balls will exceed the maximum distance of 291.2 yards? So we have to find the probability that one of the balls are going to go above 291.2 yards. So to find that probability, we have to do 1 minus the probability that all 5 distances are going to be less than 291.2 yards. So that equals 1 minus, and then 1 minus 0.1271 to the 5th, because there are 5 balls being tested. That equals 1 minus 0.8729 to the 5th, and then 1 minus 0.5068, which is 0.4932. So there's a 49.32% chance that one of those 5 balls is going to exceed the maximum distance of 291.2 yards. And all that math right there was just simplifying the parentheses down in order to get the answer. Part C. Part C asks, if the manufacturer wants to be 99% certain that a randomly selected ball will not exceed the maximum distance of 291.2 yards, what is the largest mean that can be used in the manufacturing process? So, the 99th percentile for a standard normal distribution is 2.33. So we set the appropriate z-score equal to 2.33 and solve for the mean. So the mean variable is m in this case, which was what I was using. So you do 291.2 minus m over 2.8 equals 2.33. And then we solve for m. So we get that m is going to equal 284.676. In order to be 99% certain that a randomly selected ball does not exceed the maximum distance of 291.2 yards, the mean should be set to 284 0.676 yards. And that's basically just saying that if the mean is set to anything above that value, then there is a chance that one of the balls is going to go over it, which is illegal.